difference is that an arithmetic sequence means that we are having a common difference. So we are using addition or subtraction to get our next term. And geometric sequences mean that we use multiplication or division to get our next terms. So we're going to go into that a lot more today and work a lot of problems. For that, I know we talked over some of the different values already, so let's look. There we go. Let's look at these. Are these sequences geometric? So we are intentionally looking to decide, do they have something that is a common ratio, multiplication or division involved? What do you think about the first one? 1, 2, 6, 24, 120. Is it a geometric sequence?
Yes.
Okay, I have one that says yes. Why do you say yes?
Because each one is, like 1 is multiplied by 2, 2 is multiplied by 3 to get 6, 6 is multiplied by 4 to get 24, 24 is multiplied by 5 to get 120.
Okay. So the ratio is a sequence. But what's the rule for a geometric sequence?
Has to be the same.
The ratio has to be the same.
Oh.
So if I talk specifically about the ratio, we'd say, yes, the ratio here is a sequence. But our term values are not a sequence for this one, okay? Let's look at this bottom one. 81, 27, 9, 3, and 1.
They're all divided by 3.
Divided by 3, which can also be said multiplied by
-1.
1/3. Excellent. Okay, divide by 3, multiply times 1/3, same thing. Yes, the bottom one is a sequence. So they have the same amount. Okay? So just like we were able to walk through our list of numbers, our sequences for our arithmetic sequences, and we know that to find any term in that sequence, that's our a sub n, so we've got those two different formulas. To find any term and then how to sum it up. We're going to have the same thing for geometric sequences. How to find any term and then to sum it up. So we've got different options. So just like we had our first one where we said we started at the beginning, I'm jumping by a certain amount each time. So I can find any number by starting at the beginning and deciding how many times I get there. Geometric sequences work exactly the same. We're going to start at one place. We're going to jump a certain number of times to get to the next place. But instead of our jumps being by addition and subtraction, our jumps are now by multiplication or division. Okay? So what does that end up looking like? In our case where we had 1, 3, 9, 27, so I went up instead of backwards for sake of not working with fractions, we're now jumping by 3. So if I was thinking 1, 3, 9, 27, this is term 1, terms 2, term 3, term 4. Remember, we need to write it with our bottom number as the variable of the expression, right? What am I doing? I'm multiplying times 3 each time. We are jumping up. So we're going to start at the beginning, which is our A1. And then we get to take the ratio, which is what we are jumping by. In this case, it's going to be 3. We're jumping by 3. And we raise it to how many jumps that we have. What do we notice is the same here? 5 minus 1. It's an n minus 1. What did we have up here? N minus 1 also. So every time, because our jumps are always 1 less, because we're actually counting the gaps between it, we have that n minus 1. So what I could say is that to go from 1 to 9, I've got 3 times 3. Is that correct? 3 times 3 is 3 squared. So I would start at 1, I would jump 3 times 3 and get 1 times 9 and end up with 9. If I'm going from 1 to 27, I would have 3 times 3 times 3, which is 3 cubed. So I'd start where I'm at, and I'm going to multiply it times 3 cubed. If I started at 3 and I wanted to get to 27, so I start at 3, I want to go to 27, I've got 3 times 3, so that's times 3 squared. Does it get me 27? 3 times 3 squared? What do our property of exponents say? It's the same as 3 cubed, right? Which is still 27. Right? So it doesn't matter where we start. So we are working the same thing. We are working according to the number of jumps, but because our jumps up here are multiplied, we're dealing with an exponent. Before, when it was an arithmetic sequence, these were added. So we had our D times our certain number of jumps. Right? Do you see why in this case for arithmetic we have D times it? Because they are added. Now that they are multiplied, we now have an exponent because we're multiplying them each time. Okay. So our generic parent function for a geometric sequence to find any value for the sequence. Let's see. Oh. Oh, my computer didn't die. It did die. That's weird. It was full power when we started. Oh well, you're gonna have to just take notes. And then I have them up so you can find them. Okay, so our generic form is a sub n equals our first term times our common ratio raised to the number of jumps that we have. So to find any term, we've got our first term, our common ratio, and how many jumps. Okay. Now, what do we notice? Because we have exponents involved, as long as we know what term we're trying to find, all we're doing is plugging in the n, correct? What happens when they're asking us to find the term? What is the opposite of exponents that we were learning now that we have a variable in the exponents? What did we learn in the last? The opposite is roots or logarithms, right? So this is why we learn logarithms, because whenever we have our variable up in the exponent, we have to use a log to undo it and find it. So this is how it all ties in together. Why you need one to find the other. And everyone said, boo, right? Okay, so if we have the 8th term, it said, here's our value we have. Let's evaluate this one first. So you're given this sequence. A sub n, our generic one, is -8 times 3 halves to the n minus 1. What is our first value of this sequence? What is the first value? What do you know from?
-8.
The first value is -8. Excellent. Our a sub 1, our first value is always going to be here. What are we jumping by each time? What is our common ratio? 3/2. Perfect. So we're going to find every term by jumping by 3/2. So and these are multiplied at the top. Okay. To find the 4th term, I would jump 3 times to find the 4th term if it was 4th. So if we're going to find the 8th term, what numbers do we replace? We're going to place in with 8. Let's find the 8th term. Okay. So we're starting at -8. We're jumping by 3 over 2. How many times to get to number 8 down here?
7.
7. So we're going to have 7 jumps. So we're going to have 3 over 2 raised to the 7th. Right? So at this point, it's just a matter of plugging in numbers, right? So we have -8 times 3 to the 7th over 2 to the 7th. Correct? Yes. So that gives us 2187 over 128. And that is equal to -2187 over 16. Because 8 goes into 128 16 times. -8. Okay? So if they give us a term, if they give us our generic, and they say find the 8th term, all we do is just plug in the numbers. Okay? So as long as we have a first term and a common ratio, we can write an equation for the sequence, correct? Because this is your equation for your sequence to find any term. So if I give you a sub 1 equals 2 and r equals 3, what is your equation for your sequence? What is our generic equation for any value of the sequence?
Times 3 to the -1.
Perfect. All we do is plug them in, right? Our first term, a sub 1 goes in there, so 2 times 3 to the n-1. And that says for any value, I could find the 97th value by plugging in a sub 97, and what would I put here? 97 minus 1, so it'd mean 3 to the 96. Okay? Okay, so now we have our generic, and as long as we have any one term and our common ratio, can we write our equation? So if we were given a sub 3 equals 5 and r equals 2, where do these numbers plug in? We would say first a sub 3 is equal to a sub 1 times 3 minus 1. So plug it all in straight, right? Now, can we replace a sub 3 with something?
5.
5. A sub 3 is equal to 5. So these get to be replaced. So we can say 5 is equal to a sub 1 times 2 to the 2, right? 2 squared. So now we're going to solve for a sub 1. X wants to go to the movies by himself. What do we have? 5 is equal to a sub 1 times 4. A sub 1 equals 5 over 4. Where does this now go? Back up to plug in right there. So we re-erase, because all we wanted was that a sub 1. So now we have 5 over 4 times 2 to the n minus 1. So we were able to write our generic expression given any term in a common ratio. Okay. So what if they give us 2 terms? Can we solve it? Okay. So they give us a sub 2 equals 45 and a sub 5 equals negative 1215. What do we have now? Well, let's start with our first one. What do we know when we have a sub 2? Let's take our equation and say, I know for any value, a sub 2 is equal to a sub 1 times r to the 1. Right? What else do I know? I know that a sub 2 is equal to 45. So 45 is equal to a sub 1 times r. What else do I know? We know that a sub 5 is equal to our first term times our ratio to the fourth. I'm not writing the 5 minus 1, just dropping it down. What else do I know? Negative 1215 is now equal to a sub 1 times r to the fourth. I have two variables and two equations. Can we solve this?
Sure.
Yes. Okay. So we're going to use substitution here. Let's solve for a sub 1. It equals 45 over r. It gets plugged into the second one. So now we have negative 1215 equals 45 over r times r to the fourth. Okay, what's the first thing that we simplify? What's the first part you want to simplify?
The R's.
The r's. Okay, I have r to the 4 on the top and r to the 1 on the bottom. So what do I really have?
R cubed.
45 r to the 3.
Yep, r cubed. 4 minus 1 is 3. Right, so we used either our properties where we know when they're divided they subtract, or we could say technically I had r, 4 r's and 1 on the bottom, and then those two canceled out. So a couple different ways that we got r cubed there. Okay, now r wants to go to the movies by himself. Who do we get rid of?
4 over 45.
45. How do we get rid of him? Divide both sides by 45. Right? So now I have r cubed equals negative 27. Can I take a root of this negative number?
No. Oh, yeah.
Joshua's saying yes. Why?
Because negative 27 could be because of square root and stuff.
Because my exponent is odd. Because your exponent is odd. If my exponent was even, can I take this negative root? No. Even exponents have to have even values. Odd exponents can have either even values or odd values. Correct? So the cube root of 27 is 3. But it started out negative, so it's negative 3. Okay? So do we have everything that we need to write this out now? What do we now know? A sub n is equal to a1 times, up here's my negative 3 to the n minus 1. What are we still missing? Okay, did we have something where we solved for a sub 1? Okay, so remember our whole like draw your arrows and we get a circle around when we have two equations? So we used equation 1 to plug into equation 2. So now we can use equation 2 to plug into equation 1. 45 divided by negative 3. 45 divided by 3 is what? On a clock. How much is in each of these sections? I use clocks a lot for the 5s and the 15s because from the top to there is 15 minutes, 15 to 30, 30 to 45. So 45 divided by 3 into 3 sections is 15 minutes each. Positive or negative? Negative. So we're going to plug this up here and go negative 15. All right? So now we have a full equation that we can find any term, knowing that what they had given us, that the second term was 45 and the fifth term was negative 1215. All right? So this is the other equation that you need to know along with your addition one. So for addition, we do what? A sub n plus what? What's the formula we learned that you,
A sub 1 plus A sub n.
I heard it Tessa?
N minus 1 plus times B.
Perfect. Nailed it. My first term plus how many jumps I have? Arithmetic sequences. Geometric sequences. My first term times how many jumps I have of that amount. Right? If you're given an equation or a problem and it just says, A1 equals 4, R equals 2. Which one do we use? Is this arithmetic or geometric?
Geometric.
Geometric. On your test, in your homework, on the ACT, any of those. When you see R value, it means geometric. If they say D equals 2, when you see D, we're automatically arithmetic. Okay, so pay attention to your variables and what they look like. So now that we know how to find any term in the sequence, so we have this long sequence. We had our 1, 3, 9, 27, on and on sequence. How do we add this up? We already found out that we can't use the pairing formula because it changes. If we were to graph this, when we graphed our arithmetic sequences, we found out that they looked like a line, which makes sense because here we only have exponents of 1. This is a linear equation. So when we graphed our values according to their term placement, 1, 2, 3, 4, we got a line every single time. Now that which made sense if we were adding it up, right? Because you go top to the bottom, I've got an average, top to the bottom, we have an average, we end up in the same place every time. Now, if we were to graph this new sequence, our geometric, at 1, I'm at 3, 2, 3, 6, 9, 2, I'm at 9. I'm up here. 3, I'm up here. What do we have now? What does this equation look like? Something that we learned. Does this look like exponential growth?
Yeah.
Yeah. It's all the same thing. Okay? So as we've done it before, you're like, hey, it looks the same. This is an exponential growth formula. Here's your first term. If it was a sub 0, that is our y-intercept, correct? So here's our first term. Here's our rate of growth and how much we're growing. It's the exact same as our exponential growth that you guys already learned. It's not a new formula. If we were to graph them, we're going to see that we've got exponential growth. So we can't add up exponential growth by pairing up. There is a long explanation of why it comes out to be what it is in your book if you want to read it. But the summation formula, so we've got the same relationship. So we have the sum of some value of where it starts to some other value, and then we're going to have the expression that tells us it looks exactly the same. It just means now instead of having this addition one in, we've got our exponential growth equation in there. Summation looks exactly the same. The shortcut of what it all turns out to be is our first term, so the sum of any number of terms is our first term, times, I'm going to write it how they write it. 1 minus r to the n over 1 minus r. Okay? And you might just have to memorize this one. Again, you're welcome to look in your book and show how this comes out to V. But we're gonna take our first term, we're gonna do 1 minus whatever our ratio is that we're jumping by however many times we have. So basically, we've got this exponential growth part here, and then we have 1 minus our ratio on the bottom. So when you're looking at it and you say, hey, my ratio, if it's positive, I'm gonna end up with a negative number and a negative number, right? Yeah, you will. Negative and negative equals positive. So that's how we end up with a positive number with it, okay? So let's look at this in real live numbers. So let's consider this sequence. Okay? What is our sequence here? What is our common ratio?
5.
Okay, so we know our ratio is 5. What is our first term?
No.
1. Okay, so what would be my 10th term? What would I use to find my 10th term? What on the board helps us? Since I'm not using it, I'll do that. Do we see anything up here that will help us find our 10th term? Do we need our equation to find any term? Because this is our any term equation, and this is our sum. So which one are we going to use first?
Return.
Any term, okay? So if I'm going to plug in what I have, if I want to find my 10th term, I'm going to say a to the 10 is equal to a to the 1, which is 1, times, what's my R?
5.
5 times how many jumps?
9.
9. 9 jumps, okay? So that means my 10th term is, it's a really large number, because I took my calculator and I plugged in 5, and then I hit the X to the Y button, and I plugged in 9, and I get 1,953,125. Okay? Okay. Now, what is the sum of these first 10 terms? To find the sum, I just need my first term and what I'm jumping by. So my sum of 10 terms means I take my first term of 1, and then what do we plug in? 1 minus, where's my R? 5. 5 to the what?
10.
5 to the 10. So do we see how that's different? Whereas before we had 5 to the 9th, because we're actually finding the place. For our summation, we are using the actual number of terms that we have. So we have 5 to the 10th over 1 minus 5. Right? So again, it might be some big numbers, but it's just a matter of plugging into your calculator. So we have 1 minus, and does this 1 on the front really matter? Is it going to change anything? No, so I could get rid of that. Okay, so I've got 1 minus 9, 7, 6, 5, 6, 2, 5 over 1 minus 5 is negative 4. Right? And we work that out, we get 2,404,406. Right?
Yay.
So, could be large numbers. It's just a matter of plugging them into our equation. Okay? So let's look at a word problem that involves a sequence. I'm gonna leave. Okay, let's put our summation up. Okay, who remembers what our summation is? Our first term times 1 minus r to the n over 1 minus r. Okay, here we go. So it says from 1990, so we're starting in 1990. Okay, the average monthly bill for a cell phone was $80.90. Okay. From 1990 through 1997, the average bill decreased by 8.6% each year. Okay. So those are all of our rules that we have. Okay, so this is where we start. What would we call 80.9? A1, perfect. A1. What would we call 8.6%?
Our rate.
Our rate. How would we rewrite that as something we could use?
0.086.
0.086. Excellent. Okay. So A1 is 1990 as well, right? Or sorry, value 1 in 1 is 1990. So how many terms do we have total?
7, 6.
Yes.
Count them on your fingers. 90, 91, 92, 93, 94, 95, 96, 97. 8. Because, so this is always the tricky one with dates, you know, and they always put dates up. It's kind of like the subtraction where you have to add back that extra one. 7 minus 0 is 7, but we're actually including the 0, so then there's 8. So 91 is our second place. 92 is our third place. Oh, on and on, where 97 is going to be our 8th term. Okay? So for the first one, it says write a rule for the average bill in terms of years. So we're simply asking, what is the rule for any term in this sequence? Okay? So how do we write the rule for any term? We're going to use right here. Okay? So if, I'm going to go back and address this. If our rate is dropping, this is a negative 0.86. Okay? Do we want to have a negative rate over here?
No.
Because as our graph showed, we want exponential growth. If I have a negative rate, that means I've got decay, like we're growing down here, right? And we don't want that. We're not working with negative numbers. How do I turn this negative rate into something else? How can I rewrite the negative 0.086 as something positive? Okay. The way that we do that is we're going to find the opposite of it, right? So if we have our rate is really 1 minus 0.086. So if it's going down by that much, remember how we found decay way back at the beginning when we said our decay rate is really, we always start with 100%. And if it was growth, that meant it was positive. If it was decay, it meant it was negative. So we're actually decaying here, right? It's going down. So we have to find the rate of decay. So what is our rate really? 0.914. So here's our R value that we're going to use. So we could say that for any year, we started with 80.9. Our rate is 0.914 times n minus 1. Okay. Got that? Now, if they asked, what was the average bill in 1993? So we're going to try to find 1993. Okay. What is 1993 in our terms? The fourth one. So we're finding the fourth term in our value, which means up here we change our exponent from n minus 1 to 3. And we're simply just going to solve that equation. Plug 0.914 into our calculator, raise it to the third, multiply it times 80.9. Okay? Now, if they say, when did the average bill fall to, this back. When did the average bill fall to $50? So what we now want to go A sub n equals 50, but we don't know what n is. We know it's got to be equal to 50. They're asking, when is this value $50? So we know that the first value is 80.90. We know from the second one, the fourth value, if we plugged it in, we'd get 61.77. So we keep going down. When does it end up 50? Okay. So to look at that, we're going to still use our equation, but instead we're plugging in 50. So we've got 50 is equal to 80.90 times 0.914 to the n minus 1, and we don't know what n is. Right? The first thing that we were trying to find n by itself. So what's the very first thing we can get rid of? What's the easiest part of this equation to try to get n by itself? He's got a bunch of things attached to him.
80.9.
We're going to get rid of the 80.9. We're going to divide both sides by 80.9. Okay, that's going to give us 0.618 is equal to 0.914 to the n minus 1.
Log.
Logs. Okay, I have a variable in the exponent. I get to choose to take the log of anything, right? So if I take the log of both sides, I'm going to take the log of 0.914 on both sides. Log of 0.914. Why did I do that?
To get rid of it.
To get rid of it, because when the base and the equivalent value match, it disappears, and all I'm left with is the exponent. So now I get to erase this whole side and say n minus 1. Now I have two logs over here. What do we use to get a number? Change the base formula. Remember, we can basically put a division sign and say I can use my calculator and use log 10 of 0.618 is the same as log 10.914 and actually get real numbers for that. Okay. And that will give you a real number of 5.35 is equal to n minus 1. So what is n equal to? Is n by himself yet? That's what we keep asking ourselves. We want a value for n. Is n by himself yet? No. What do? We're going to add 1 to both sides. And so we can say n is approximately 6, right? Because it would be 6.35. So we're going to round down. So we're looking at the sixth term. What do we know? What would be our sixth term here?
1995.
95. So in 1995, the bill was $50. Average $50. But we had to use logarithms because we didn't know when. So that's the whole point of us learning logs. So now we can use it to apply here.
Could have logically guessed 6 though.
You could have logically guessed 6,
Yeah.
yeah. A lot of times you can logically guess and come out pretty good on it. I'm going to plug in. Because everything is dying today. All right, any questions on that one? I'm going to leave it up there for a minute. Is there's still a plug over behind you, Joshua. Sometimes that plug doesn't have anything in it, that extension cord.
No, there's nothing in it.
Can you grab that for me? Thank you, sir. There we go. Okay. Alright. So that is our wrap up for 11.3, which is specifically just geometric sequences. We are needing to memorize our summation formula, right? Our any term formula makes sense, like logically we can figure that out. It's good to memorize it, but logically we can figure that one out. These are the two formulas that you will need for that. So we need to know how to sum up a geometric series, how to recognize a geometric series, and how to find any term in the geometric series. So this has all been fun because we've had finite terms. So remember we said there were two different types of sequences for each one. We had finite and we had infinite. All right? So some they go on and on and on and on forever. Some they don't. Now, if we're thinking about an arithmetic sequence and it goes on and on and on and on and on and on forever, will we ever get a finite sum if we have an infinite series?
No.
No, because we have this linear line that's going on forever. There is no boundary to it. Remember that word that we found with our graphs of asymptotes? Those were those boundaries of which it approached. So there's no boundary. So when we're dealing with arithmetic series, if we have an infinite one, there is no sum. So you don't even have to worry about that. Okay? When we're dealing with geometric series, there are two options for that. So let's look at it. When we had our exponential growth, if it is exponentially growing, okay, which means that our ratio value, what do we know, had to be greater than 1. That's from our exponential growth chapter that we were learning about that. So if it's greater than 1 and every term is always getting bigger, are we ever going to be able to add that up? No. You will not be able to have a sum for an infinite series when your growth is greater than 1. Now, whenever it was less than, we found out that that just looked like logs, right? And a log graph looked like that, right? And it has an asymptote that it approaches. So when our rate is less than 1, does this mean negative? No. Less than 1 is like between 0 and 1, right? So we're looking at fractions here. When it's less than 1, it will reach an asymptote. And so we will be able to say it approaches adding up a certain amount of that. And the reason that that works like that is everyone pull out a sheet of paper. Okay. What I would like you to do is fold that paper and tear it in half.
Hamburger or hot dog?
What?
Which way?
I don't care.
Hamburger?
I do not care. Fold this paper and tear it in half.
Vogel.
Then fold each of your halves. Tear them in half. Does this remind you of the Twizzlers? One. Right? Then fold each of those 4 and tear them in half. Okay, I need to teach you guys how to fold, slide your fingernails, and then it'll tear nice and clean. Now, when you get about 8 pieces. You can stop. I don't see you tearing, Jace.
Hmm?
I don't see you tearing.
Okay.
You're tearing.
Yeah, fine, okay.
Well, without this candy pieces.
That's why I hide my trash.
Keeps me focused, keeps me engaged.
Alright,
Like 2 of them are Jace's, so.
we're 2 or Jason. He just threw you under the bus. He
Well,
just
you
threw you
had
under the
like
bus.
2 Jolly Ranchers.
Okay,
No, I
so do we have all of our papers
Oh, yeah,
torn?
okay.
What have we been doing with our paper when we're looking at our growth or decay graph? Having it. Excellent. So if I looked at it, I could say that technically my A1 is 1, right? And my R value here is 1/2. My R value falls within this 0 to 1. It's less than 1, and I'm getting half of it. If I asked you to add up all of your pieces, start putting your pieces back. Add all of your pieces back together. I heard an extra tear. When you add all of your pieces back, what do you end up with?
A very broken piece of paper.
How much of a piece of paper?
1/8 of it.
When they're all added together?
Oh, one paper.
When they're all added together, you end up with 1 whole paper, right?
Oh, yeah.
So we end up back at the beginning. Now, if we got down to where we were, the pieces that we were adding back were these little bitty tiny pieces, okay? Would it be fair for me to say that I'm pretty much adding nothing back to this? So if I had a whole paper and then I start adding, I'm saying, okay, well, I'm adding this up or whatever it was adding, and the amounts, because the amounts that we're getting, each time, you know, for this 8th one, I added a piece that was this amount, and it added something to it. Now, if I took, you know, someone else has their paper where it's added together, or it's a 16th piece, and I added to it, it would add something to my paper, correct? And then, you know, Aaron has his paper torn into 30 seconds, and I add one of his 30 seconds, it would add something to it. Tessa gives me a 64th, you know, then Joshua gives me a 1 1/8, and I keep adding those pieces. The amount of pieces, by the time I get down, Will says, here you go, Miss Thomas, this is what I have to offer. And he gives me this little piece. Did it add very much to what I have? Okay. And then we tear that one because the next section is now this tiny piece. And that was Joshua's section. He says, here's my contribution, Miss Thomas, and he gives me this little one. And then Miss Lowe's got in on the fun, and she had the next one, and she gives me her piece. Here, I've got something to add. And then Eden gives me her piece. I've got something to add. Are you essentially adding anything to what I have?
Yes.
I mean, is that going to change my value?
A little bit.
A little bitty bit.
I'm just
Yeah, a little bitty bit. But in essence, we reach a point. You're eventually gonna reach a point because the pieces are getting smaller and smaller and smaller, that we are, in essence, we're not really adding anything extra to it. Does that make sense? So as we go along in the sequence, and our sequence is a decay sequence, so we start with, not that. We start with 1, and then we have a half of a piece, and a fourth of a piece, and an eighth, and a 16th, and a 32nd, and we move all down, we end up with like, maybe I'm giving you a 256th piece. Does this, now when I do 1 plus 1/2, that's 1 1/2. So I've got 3 halves plus 1/4, like, it started growing, and I had, so many pieces, or maybe so many apples, or so many donuts, or whatever in there. But now when you give me your 1 out of 256th piece, does it really change how much I have?
Not really.
No, it doesn't really change. So there comes a point to where it just evens out. And that's why it looks like the log graph where we had those asymptotes. And we said, it really just kind of, it's going to level out. So when we have an infinite geometric series, and we are trying to sum it up, if our pieces are getting smaller and smaller and smaller, there reaches a point where, in essence, we're not adding anything extra. And from that point on, it's not going to change the value. So we can call it a sum. We can call it a finite number because we're just adding 0. We're adding nothing to it from that point forward. Okay? And the formula to find that looks very similar to our summation formula, except that we lose the top. All we do is lose the top. Okay? So our summation for an infinite series, I have no subscript. If I put a subscript, I would put infinity, meaning it goes on and on and on and on forever, simply states that wherever we start, we're going to divide it by 1 minus our ratio. Okay? So when we have a finite series, we're going to tie it into how many we had. When we have an infinite series, we don't need to know how many we had. That's why we lose that top part. Okay? Because we have infinitely many, and all we have is ace of 1 over 1 minus r. So let's look at what that looks like. And I think it's important, that the reason I did the paper thing is so that you understand, if I say, oh, you're just never adding anything more, we see that what we're really adding is so minuscule that it doesn't matter. Then you're like, oh, okay, that makes sense. We're going to even out at some place. Okay, so if we have the summation of I1 to infinity, our infinity tells us that we now have an infinite series of 3 times 0.7 to the I minus 1. Okay. I know this is geometric because I have an exponent. Okay. Because we can have multiplication with an arithmetic sequence, but because my variable is there in the exponent, this is a geometric sequence. So the first thing is we've got to decipher our instruction guide. Our instruction guide says we're going to add up our term values from our first term on into infinity of what? What is my first term? What is a sub 1 here?
1. Like 0. I lost it.
Okay. If this is our
3.
generic formula for a geometric sequence, and it says to find any term, remember, our whole value,
Oh,
to find any term, our a sub 1 is equal to 3. Our r value is equal to 0.7. Okay, and then n minus 1 is simply the I minus 1. So, first, can we find this sum?
No.
Maybe.
Joshua's saying yes. Can we find the sum? Yes, our R value is 0.7. What is the rule to be able to find the sum?
Add.
R has to be a fraction, right? It has to be between 0 and 1. Now, if I said
Oh, yeah.
3 times 2 to the I minus 1, can we find this sum?
No.
No, because we have an R value greater than 1. But because my R value was 0.7, then yes, we can find the sum. It is less than 1. So how do we find it? We're simply going to plug it in. The sum is 3 over 1 minus 0.7. It's not super hard, right? So we have 3 over 0.3, which gives us 10. So as we start adding up these numbers and we had our sequence values, there would come a point to where once we got close to 10, once we had gathered enough that added up to 10, we're not really adding anything else past that. Okay. Let's look at this one. If I have 1, negative 1/4, 1/16, negative 1/64, on and on and on. Okay? What is my a sub 1? What is our first term? 1. What is our R value? How do I get from 1 to the next one? Perfect.
Yeah.
Negative 1/4. And if I do negative 1/4 times negative 1/4, do I get 1/16? Yeah. 4 times 4 is 16, and negative times negative is a positive. Right? So our R value is negative 1/4. So what is the sum? What would all of this add up to? We're going to plug in a sub 1, which is 1 on top. On the bottom, we have 1 minus negative 1/4. Minus a negative gives us a positive. So really have 1 over 5/4, which means we just flip the bottom, right? And we're going to end up with 4/5. Okay. So if they give you the sum, so in the same way as before, we can work those different things. If they give us the sum in the first place, and then they give us the first term, can we solve for the ratio? So say they say the sum is equal to 10, and the first term is 4. How would we rewrite this equation? Where does the 10 go? They're telling us it's a sum. The 10 goes in the first part, right? So the sum of 10 is equal to 4 over 1 minus R. And all we do is solve for R. Solve for our unknown. In this case, we can cross multiply or flip that and say 1 minus R equals 4 over 10, which equals 2/5. So 1 minus 2/5 is equal to R. So R is equal to 3/5. Right? So that's just simply solving there. Okay? Now, they talk in your book about repeating decimals. It's kind of a little sideways one. It is a question on your test, so I want to address it. Okay. Did anyone learn a rule for writing repeating decimals?
Yes.
You did? Okay. What was the rule? Do you remember?
You like the little line thingy?
Yes. So we have a line.
Oh, yeah.
Okay. How would we write that as a fraction?
Oh, I don't know.
Okay. So mathematic rule, if I have 0.3, that really tells me I have 3 in the tens place. correct? Because this is tens, hundreds, thousands. If I have 0.36, I would write that as 36 in the hundredths place because that's this section, right? The 6 is the hundredths place. Okay. The trick for writing repeating decimals is when they repeat, they're real close to that 10th, but they're not quite. So what's the next number that's real close to 10 but not quite? It's a number right before 10. 9. Okay, so if I have 0.333333, we say that this is 1/3, correct? I could also say it's 3/9, 3 in the 9's place, which simplifies to 1/3. So all repeating decimals, if I had this, what part's repeating? The 18. If it wasn't repeating, it would be 18 with 100. It is repeating, so it's 18 with 99. If there's 3 places, it would be 999. We're going to write the 9s in. Okay. The reason that we get here is actually from our geometric series summation formula. Okay. It shows us how to repeat it. Because, and I want you to use you're welcome to use the shortcut. I'm just going to show you why they say that. They have rewritten this by saying what it really is 18 times 0.01 plus 18 times 0.01 squared plus 18 times. So back in the day, sometimes your teacher would make you take 365 and write it out. Maybe where this is really 300 plus 60 plus 5. Did you ever have any teachers that made you do that?
Yes.
Okay, where you're breaking out each section. And so that's what they've done here. Is that they're saying when we have a repeating decimal, we are just breaking it out and showing that all we're doing is adding a whole bunch of pieces together. And our geometric series gets us that. If you're writing a repeating decimal, I prefer just use the 9s trick for that. Okay, so one more little section. This is pretty easy. We've got 5 minutes. Okay, recursive sequences. Okay, recursive means that means we're going back to what was before and we're writing it again. So if we want to look at the semantics of it, recursive, we are rewriting from what was before. So if I have 1, 2, 4, 8, on and on and on, or if I have 1, let's do our odd one that we were doing. We already know how to find a certain value in the sequence, right? Those are ones we have learned. There's another way that we could write it is we could talk about every single place in relation to the number right before it. So that's what it means for recursive. Recursive means instead of looking at the beginning or looking at your entire system, it means to write an equation for your value or your term that is related to the number that is right before it. Or maybe 2 terms before it. Fibonacci sequence is 1, where the next number are the 2 terms before it get added together. So for this next term, I'm going to add these 2. For the next term, I'm going to add these 2. So our next number might not be related to the beginning. Our next number in the sequence may only be related according to a number right before it or 2 numbers right before it. Right? So to look at a recursive sequence, there is a formula for a generic, and we're going to look at how it's different. To find any term in a recursive sequence, we're going to take the number of terms. We're going to take that term. This is for a geometric one. And we're multiplying it by the term beforehand. N minus 1. Does it look like it's just the opposite? that instead of your A value, you now have your N value, and then instead of your R value, you now have your A value. All we've done is switch them. That's basically all you're doing. So if we had A sub 1 or A sub 0, and they always start with A sub 0, or they'll say A sub 1, they'll give you 1. Okay? If we have this one, N times N minus 1, that means for my first term, we're going to have to relate back to the term right before it. So if I'm looking at the first term, I'm looking at the 0th term. If I was dealing with the 8th term, say my N value is equal to 2. I'm jumping by 2 according to my 7th. So I'm going to take my 7th value and I'm going to multiply it by 2. So we've taken our long sequences and we're breaking it down into just one little section and saying, how did I get to this next number? How did I get here from right before it? Instead of how do I get here knowing the whole process along it. So we're going to address terms as far as either the term right before it, like N minus 1, or a term before that. The one that is important for you to know is the Fibonacci sequence. 1, and they will give you something like this. So the first term is 1, the second term is 1, all of the subsequent terms are N minus 2 plus N minus 1. So this looks super confusing, but let's think about what it means. If I were to find the 5th one, that means I'm going to add 5 minus 2 is 3, 5 minus 1 is 4. I'm going to add 3 and 4 together to get number 5. So don't get confused when we are in the variable format of the n's. I always just go ahead and plug a number in so that my brain can think about it. It's like, oh, to find any term, I'm just adding up the 2 terms before it. So let's just do 1, and then I will let you guys go. This is called the explicit rule, a recursive rule. So we have the explicit rule would be your arithmetic sequence or your geometric sequence. The recursive sequence is related specifically to the number right below it. So if we were given A sub 1 equals 3, and my relationship relates like that, A sub n is equal to the number before it plus 5, this looks like an arithmetic sequence, right? I'm taking the number before it and I'm just adding 5 to it. So what would be the first 4 terms? We know the first term is 3. The next term would be, the second term would be A sub 2 minus 1, my first term, plus 5. My first term was 3. 3 plus 5 is 8. What is my third term? I'm going to take the term before. Third term is 8 plus 5 is 13. 13 plus 5 is 18. It is simply a different way of writing the same exact sequences that you guys already know. You would say initially, my arithmetic sequence means I take my A sub 1 plus however many left. So I would have 3 plus N minus 1 times 5, right? Because that's my jumps. My recursive sequence says just take that term and add 5 to it. So we've broken it down into a smaller section relating the terms to each other. Okay, that's all that it means for this. All right, you guys did really great today. I will put up little individual videos on each of the sections if you want to have more instruction. And then you will have your homework, and then I will also send out the test problems for it, and then I will see you guys in 2 weeks. Oh, those are my notes. And and then extra homework, extra workout problems if we had time. But we never have time.